Thank you, Baptiste. Thank you very much for the introduction and for the invitation to join you here today and tell you a little bit about some of the work that's ongoing to explore some ocean worlds in our solar system. Can you guys hear me all right? Yes. Great, okay. Feel free to interrupt with questions. I'm happy to make this really informal, however you guys would like to do it. So as Baptiste said, I started off in chemistry, and as any of you who are working in astrobiology-related fields know, it's a very interdisciplinary type of work. So some of the things I'll be talking about today may cover some aspects of biology, chemistry, physics, astrophysics, geophysics, all of that. But first, let's talk about what an ocean world is. I mean, many of you probably already know the answer to this, that most ocean worlds in our solar system do not look like Earth. Earth, yes, it is an ocean world, but most of the other ocean worlds in our solar system tend to follow this paradigm, where you still have a liquid water ocean. Usually it's water. Sometimes there may be other solvents that we can invoke. Most times it's global, but not always, and it tends to be covered with a layer of ice of variable thickness and variable composition of contaminants in that ice depending on the body. Now, when it comes to astrobiology and looking for places where life could potentially take hold or start to colonize if it comes from somewhere else, the interaction of that liquid water with a rocky core is important. So some of the worlds that are ocean worlds may be less appealing from an astrobiology perspective if they have a layer of high-pressure ice down at the base of the ocean. Now, there are lots of ocean worlds around, right? There are some in orbit around Jupiter, Europa, which I'll spend a little bit of time talking about today. Also Ganymede, which is the largest moon in our solar system. We'll give it one win because Ganymede and Callisto both, we believe, do have one of those layers of high-pressure ice down at the bottom of their oceans. And so interaction between that ocean and the rock may be hindered slightly because of that ice layer. But not just around Jupiter. We go further out. I'll spend a little bit of time talking about Titan today. It's one of my favorite places, as is Enceladus. So stay tuned for a little bit more discussion about that. But there are a few other moons that seem to also have evidence of liquid water oceans. Mimas, which we fondly refer to as the Death Star moon, may indeed hold some liquid underneath its shell of ice. And there's some tentative evidence for a few other moons of Saturn as well, Dione, Tethys possibly, a few others. And when you step further out, I mean, liquid water, thanks to missions like Cassini, Voyager, and New Horizons, we are finding that there could be liquid as far out as Pluto. Triton, which is Neptune's one of its most fascinating moons, the one that's orbiting in the wrong direction, which just blows all of our minds. It's got cryovolcanic activity. It may have a liquid water ocean that's very ammonia-rich. This is a fascinating place we should certainly go back to. And even Pluto, which might have a liquid water ocean that's being insulated by a layer of methane clathrate hydrates. You guys know what that is? That's where water essentially forms a cage. It traps a methane molecule inside. And it turns out the thermal properties of a clathrate like that are very different from regular water ice. And this layer could be keeping a liquid water ocean on Pluto. It could be keeping it liquid for on the order of millions of years. So ocean worlds can be diverse. They can exist in many different places, and we're still starting to understand those properties and how that might affect where and how we might search for life in our solar system and beyond. So let's dive a little bit more deeply into a couple of these ocean worlds. So I've been loving all of the images that the Juno spacecraft has been sending back of Jupiter, which in itself is a mystery wrapped in an enigma? Isn't that what Churchill used to say? But I think its moons are even more mysterious. So Europa it's not a huge moon. It's about the size of our moon. If you were standing on the surface of Europa, you could imagine yourself feeling about the same gravity that the NASA astronauts felt when they visited our own moon. The light would be, let's see, it's about 20% the brightness as it is here on Earth, if you were to look at the sun. And you would get a lethal dose of radiation in a fairly short amount of time. Luckily for us, though, that radiation is actually shielded, the ocean underneath is shielded by the thick ice layer. It turns out you only need a few centimeters to get rid of most of the types of radiation that are present in and around Europa. Now, this radiation comes from Jupiter, which has a giant magnetic field, and it basically takes particles from the solar wind, protons and electrons, and it captures them with its magnetic field and slams them around, most of them into the backside of Europa, actually, which is why we see that asymmetry in color. One side of Europa is a lot darker, and the other one is a lot lighter. Now, for implications for life, this is actually a good thing. What we think is happening at Europa, which has a liquid water ocean of about 2 to 3 times the volume of all of Earth's oceans combined, this liquid water is, we think, in contact with the rocky interior. Now, when this happens, you can have things like hydrothermal chemistry. You can have other sort of geothermal processes that can enrich that ocean in reduced species that are rich in hydrogen, rich in electrons, and this means that now you have a place that has a very reducing condition down at the sea floor. Now, up at the ocean top, where now you're in contact with the ice, you're potentially having a lot of charged particles, radiation that's impacting the surface of the ice. Now, this can hit water and break it up to form things like hydroxyl radicals. You can form hydrogen peroxide, things like that are very oxygen rich. And when that happens, if they are able to move down into the ocean, now you have an oxidized area right at the top of the ocean. So basically, you have a giant chemical battery, right? You have an electron-rich region down at the bottom, an electron-poor region down at the top. And so any way that you can facilitate moving those electrons to the place where they're concentrated, to the place where they're not concentrated, now you have energy that life can utilize. Mike Russell, who's an astrobiologist who used to work at JPL, liked to say that life was basically our one creative way of sort of helping the universe establish equilibrium. All we do is shuttle electrons around, which is kind of, I don't know if you would call that poetic. I think it is. But so Europa is this fascinating place, right? And it's got so many incredible things happening on the surface that we think are connected to the ocean below. We see areas of chaos terrain where it looks like something was floating and someone smashed it with a hammer, and these pieces of ice broke apart and sort of floated around and then refroze. We see regions of smooth bands where it looks like the ice cracked apart and spread open, and material from underneath came up and refroze. Also, we see very few craters on Europa. Now, this is typically how we date things in our solar system, right? This tells us the average age of Europa's surface is probably only around 50 million years. Now, that sounds very old, but compared to the 4.5 billion-year-old age of our solar system, it's very young. And so this tells us that there's exchange happening, that the surface is relatively fresh, which means if we were to sample from that surface, we may get a fairly decent idea of what's going on in that ocean below, as long as we are very careful about interpretation of what has happened to that sample in between when it was in the ocean and where it is today. And luckily, NASA also agrees that this is a fascinating place, and so the Europa Clipper mission, which is now in phase C, is moving forward. This mission is going to launch in 2025. Depending on the rocket that we go on, we could enter into Jupiter orbit insertion anywhere from like 3 to 6-ish years from that point. Now, the Europa Clipper mission is going to orbit around Jupiter and do flybys of Europa to basically stay out of that radiation zone. So we get in, we get some nice images, collect some good data, and then get back out where the radiation is less intense. And we'll do that many times. It's going to be really exciting. Anytime you send a mission like this, a very large flagship class mission, you end up having more questions than answers at the end. And I cannot wait to see the new questions that arise from the incredible amounts of data we'll be getting from this mission. Now, not only that, though, Europa Clipper is going to be incredible, but it is not going to land on the surface. We will get some particles sputtered up, but ultimately, if you really want to address this life question, you really need to get down there and touch, taste the surface. This is a video of a concept, a mission concept called Europa Lander, which some of you, may be familiar with. This lander would touch down on the surface. It would take advantage of the data set from Clipper, but it wouldn't necessarily need it. The engineers at JPL are very creative at coming up with ways to land in environments that may be rather steep or rocky or otherwise treacherous. This lander would then be able to use some type of cutting tool, which the engineers have been having a really fun time trying to come up with something that can handle ice at these temperatures, which in many ways has some properties similar to granite at about 80 Kelvin, could cut in, collect a sample or multiple samples, and bring them in to analyze with a bunch of different instruments. There is a NASA call that came out called IC2. This is instrument concepts for exploration of Europa to support some instrument development for a mission like this or similar to this, where we would be on the surface looking for either ingredients of life or evidence of habitability, or just trying to understand that environment. But hopefully something like this could be possible in the near future. Now, what would a mission like that look for? Well, of course, life is important. And I'll talk a little bit more about the life question in a minute, but none of that matters if you don't understand the context of the measurement, right? So assessing the chemistry of an environment, making sure that indeed the life measurements that you're detecting, let's say that you find some sort of extremophile that's a sulfate reducer, but you find no sulfur chemistry going on, that sulfur's not even present in your environment. Well, how confident can you be that that detection was real? Maybe you brought that microbe along with you. Contamination control and planetary protection are big questions that we have to make sure we've reduced the risk of whenever we try to explore these environments. So understanding the habitability and the context of that measurement are really critical. Now let's dive a little bit into that life question. We all are familiar with the Viking missions that landed on Mars back in the late 1970s. Viking had 3 different life detection measurements. One was positive for life, one was negative, and one was ambiguous. So where does that leave you? And it's not like the engineers and scientists who designed Viking weren't doing their absolute best. It's just they were operating off of limited information. At the time that Viking landers were built and landed, we had no idea that archaea was a thing. We only knew about 2 of the branches of life. PCR hadn't been invented yet. And in fact, I don't even think hydrothermal vents had been discovered on the ocean floor yet. So we know a lot more now than we did then. Doesn't mean that we won't make the same mistakes, though. We'll try not to. We'll try very hard. And one of the ways that we can do this is by coming up with multiple independent tests for life. So bringing along instruments that can assess completely different biosignatures. Maybe one is looking for organic molecules that are consistent with life, patterns like amino acids or chirality. Another one could look for evidence of cells or other morphological indicators of life. One other might look for inorganic indicators, like let's say you did find a sulfate reducer and then you found sulfate minerals that were characteristic of that type of organism, those kinds of things. And hopefully we'll get to a point where we can be talking about the detections that a landed instrument or a landed mission like that has made. So now I want to go out a little bit further, actually a lot further. You know how they always show those like the diagrams of the solar system, and like the sun is here and then the planets are like evenly spaced out? You know, that's not true, right? Like you go from the sun to Jupiter, you do that again to get to Saturn. Space is big. But that's okay, because that means there's a whole lot to explore. And one of my favorite moons around Saturn is Enceladus. This is one of the iconic images taken by the Cassini spacecraft, which I was really lucky to be a part of. Cassini launched in '97, got to Saturn in 2004. Space is big. And was in the Saturn system until 2017, when it did its graceful swan dive into Saturn on purpose. Who knows why we did that? Why did we crash a perfectly good spacecraft? Anyone? Marshall?
To prevent contaminating someplace like Enceladus.
Exactly, to prevent contaminating someplace like Enceladus. Now, when Cassini was built, we had no idea that liquid water could exist out this far. So we cleaned it, but we didn't sterilize it. The restrictions in terms of cleaning and sterilizing the spacecraft, Cassini was what, a Cat 2, I think, which meant, you know, don't like sneeze on it, don't cough on it, but, you know, we're not going to do all of our high-degree bake-outs and things like that can be expensive. And so because of that, Cassini was sort of a victim of its own success. By the time it had finished exploring the Saturn system 13 years later, we knew there were multiple places liquid water was currently present in the Saturn system. And we didn't want it to run out of gas, which it was doing. It was on E. The engineers were placing bets as to how much fuel was left. Some of them actually modeled it and thought that Cassini might have exploded a little bit in the Saturn system, like when it was going in, but we never got to see it. There's still just theories. But it was basically on empty, so no fuel left. What if we had let it completely run out of gas? We would not be able to control the spacecraft anymore. Now it can just drift on its own. It's not going to leave the Saturn system, but we can't control where it is anymore. Maybe 1,000 years from now, maybe 10,000 years from now, it crashes right at the south pole of Enceladus. Oops. What if some organisms from Cassini were to end up in that ocean? I certainly want to be on the forefront of finding life for the first time in human history somewhere else, but I don't want to find out later that we put it there. And so Cassini, though, gave us some amazing information before its demise. And we got data all the way down. We're still analyzing that, which is great. So that's one of my favorite images of Enceladus. This is another one. This was actually taken by Voyager 1 and has since been modified by a colleague, Ted Strick. I'm going to just zoom in here. Do you guys see that little tuft at the bottom? So although Cassini is, of course, credited with the discovery of the plume of Enceladus, it does look like Voyager 2 was actually the first spacecraft to capture an image of it. It just took modern-day processing capability in order to pull it out, which is kind of cool. So Enceladus is not a huge moon. It's about the size of Arizona, and it's got these 4 big cracks down at the South Pole. All the features of all the planetary bodies, they each kind of have a theme. Like Mars is sort of war and stuff. Venus is all, famous women, I think. All the features are named off of it in history. Well, at Enceladus, for some reason, all of the features are named after the 1,000 Arabian Nights tales. So there's like Baghdad and Cairo and things like that. I still don't know why. If anyone does, come find me later and tell me the story, because I've asked everybody, and no one seems, not even Candy Hansen knows. But yeah, the 4 tiger stripes, they are about 130 kilometers long, something like 30-ish kilometers apart. And out of them is spewing free sample from Enceladus' ocean into space. There's a gas component and a grain component. Both of them, we were lucky enough that Cassini was able to fly through and sample with its 2 mass spectrometers. So you can kind of picture this as like sticking your tongue out, except your car is moving at 7 kilometers a second, and the ice grains are, that might be a little dangerous. I don't recommend doing that. But the spacecraft could handle it. Now, for the plume gas, Cassini's ion and neutral spectrometer, mass spectrometer, was the instrument that did these measurements. We found a few very interesting things, including methane and molecular hydrogen. Now, these are important because these are molecules that certain types of microorganisms can use to metabolize, or their outputs, right? Methanogens generate methane. Methanotrophs use it. But it's still very exciting to know that these types of molecules exist. We were also able to measure in the grains, which are mostly water ice. There is some salts that tell us a little bit about the salinity of Enceladus' ocean. But we also found what we call these high-mass organic cations. Now, the way that the cosmic dust analyzer, which is the one that analyzed the grains, the way this instrument works, it's a time-of-flight mass spectrometer. That means ice grain comes in, it smacks into a plate. I think it was made of rhodium. It was a rhodium plate, and it vaporizes. And some of those molecules inside ionize. This is great. Once they're ions, now we can move them with an electric field, and so we can shoot them down a tunnel, basically, a time-of-flight tube. And depending on how big they are and how charged they are, they'll take different times to get down that tube. Problem is, though, the longer the time of flight is, the worse your resolution is. And so by the time we get to these beautifully spaced things that are way out here that just happen to be a unit of 12 apart, what element is mass 12? Carbon. Oh, that's really interesting, isn't it? But our resolution here isn't to where we could say these are proteins or these are a certain type of molecule, although Frank Postberg and others do have some very convincing evidence to suggest that some of them may be aromatic, so we may have some rings in there, we may have some nitrogen character, but we really do need to go back. So we've got this tantalizing picture right now of what Enceladus looks like. It's got a global liquid water ocean. The crust is a little bit thinner on the south pole than it is on the north. We do have evidence of hydrothermal vents, in this case a little bit more well-constrained than Europa. Part of this is because of something called these silicate grains, SiO2. So, or silica, not silicate, sorry. Silicate is SiO4. Any geochemist in here, please forgive me. These were also detected by the CDA, the Cosmic Dust Analyzer of Cassini. Now, these grains, because of the certain size that they are and the oxidation state, based on modeling, the only thing that could form them is interaction of liquid water in contact with a rocky core at temperatures of 90 degrees C or above. That's almost boiling point of water. Now, these are images not of Enceladus, but here on Earth, of a hydrothermal system called Lost City, which is alkaline, so it's high pH, similar to what we think the Enceladus Ocean is. And in this hydrothermal system, not only do you find microorganisms, you find a rich, diverse community, including things like crabs, tube worms. It's not octopi. What is it? Octopods? What did we decide? Octopuddles. Octa something. But the point is that you find these diverse communities that are living as far removed from sunlight as you could imagine. Because remember, all of these ocean worlds out in the outer solar system, sunlight is either incredibly dim or non-existent because you've got this ice crust shielding you in the ocean below. So again, we've got an environment that seems to have all three ingredients for life as we know it: water, chemistry, and energy. And it would be great to go back. Now, this is a digital elevation model that's been generated by Paul Schenk, and this is of Damascus sulcus, which is one of the 4 tiger stripes. And one thing I want you to notice is that in some places, it looks like some of the chasms, the cracks of the ice seem to have been filled in a little bit, right? And this makes sense because Enceladus is, it's spewing out ice grains of various sizes, and the larger ones are going to settle back down and sort of a nice, soft, fluffy snow. The gravity at Enceladus is 0.01 g, so 1% of Earth's gravity, so it's really light. Well, what? The scale, it's about, it's like 200 meters wide at that widest part of the trough. Does that help? And about, I don't know, probably 150 meters high at that highest point. Does that help? I'll put a scale bar on there for next time. But the point is, any sort of standard rover, well, first of all, a lot of these angles may be a bit too extreme for a rover to go up. I think the steepest angle that you can successfully drive, for example, a Mars rover up is about 20 degrees-ish. I think they tried a 32-degree slope once and had to turn around because it was too steep. Not only that, but you're moving through this like fluidized media kind of bed, right? This is not traction may be an issue. So one of the things that we've been working on at JPL is ways to potentially move through something like that, where there could be many different visions of what the surface of Enceladus might look like. It might be like creme brulee, where you've got this sort of crusty bit and then soft stuff underneath. It might be fluidized media like this. It might be something else. The point is we don't know, and so we need to design some kind of architecture if you want to get down on that surface that would be able to handle all of these things. Well, we're working on a concept right now that might be able to handle that, and this is a video that was made in collaboration with someone who also did some of the animations for the Avengers film, showing a concept that could potentially address any of those types of environments on Enceladus. You'd have some kind of a landed element so you could communicate back to Earth, and then you could have something like this. We're calling it the Enceladus Extant Life Surveyor, or EELS, because snake sounded a little too creepy. But essentially what you have is a vehicle that can move forward and backwards because it has these rotating bits around each of these segments. You have an ability to potentially modify the segments for what have you. You could include different payload elements in them. You can include battery, power, heating elements if needed. You could even have some of them have chunks of the tether that you would use if you wanted to stay tethered. There are various versions of this that could be tethered or work autonomously. Now, when it comes to material coming out of the plume of Enceladus, this is happening at about 200 meters per second. And essentially, the forces of that gas and grains pushing up is about equivalent, if you do the math, to if you were to be pushing up against Earth's gravity, sort of going up against the force of gravity. And so this could push up against the walls and sort of function like an Archimedes screw to move down against those forces. There are 2 leading theories for how the vents work on Enceladus. One of them has like basically a 5-meter wide chasm that kind of pumps with the orbit of Enceladus. Another version has a much thinner choke point over some sort of like cavern, and some design like this could be designed to be that minimum diameter, so you wouldn't need a giant melt probe to get deep down into the depths and reach the ocean of Enceladus. Now, this is just a concept, but it's an idea to help challenge your thinking in terms of how we might access an ocean like this, whether we even need to access. Maybe we can just sit and sample from the plume at the surface. But the point is, engineers can be very creative, and it also gives some of our summer students some things to work on. This is a prototype that some summer students made last summer, just to illustrate the concept, the mobility concept for something like this. And so you could envision at some point having a data set like this, where in addition to the imaging that you could have on the nose, you could have proprioception, so sensors all across the body of this to help you orient, be able to determine how you might navigate down through a crevasse like this, and potentially sample as you go. So again, this is just a concept, but it's pretty fun to stretch your imagination a bit as you come up with what our future in situ exploration technology might entail. So now let's go back. We're still in the Saturn system, but now let's look at a different moon. Last but not least, my favorite, Titan, which is the largest moon of Saturn, and technically, if you count its atmosphere, it's actually the largest moon in the solar system. But again, we'll give Ganymede a win because, Ganymede needs something. Titan has an atmosphere just like our own. It's very rich in nitrogen, although there are a lot of other things that are quite different. If you strip away its atmosphere to look at the surface, just like a lot of these other ocean worlds, its surface is actually water ice. However, here, because of all this cool photochemistry that's happening in the atmosphere, you end up with this veneer of organic stuff covering that ice. We're not sure how thick it is. We're not even sure exactly what it's made of. That's one of the things that we're still working on trying to understand. One of the other really fascinating things about Titan, this is an image that Cassini collected, and you see that spot right at the top of the North Pole? That is specular reflection. That is reflection of sunlight off of a liquid methane lake that's in the North Pole of Titan. Just like Earth, Titan actually has a hydrologic cycle, but hydro doesn't refer to water here, it refers to hydrocarbon, methane and ethane. When I give talks to kids, I say liquid farts, because that's basically what it is. And hey, I still got a couple chuckles, so that's good. Just like here on Earth, how water forms clouds and rain and snow and things like that, we see clouds on Titan. We see evidence of river channels and other places where this liquid, different liquid, but it's doing the same sorts of things on Titan as it does, as liquid water does here on Earth. Again, the scales are a little bit different, but overall, we still see some similar processes. We have these lakes and seas that happen in the poles of Titan. On the South Pole, they're primarily ethane-rich, and the North Pole, they're primarily methane-rich, and they're large, right? These are on the order of our Great Lakes or larger, so these are substantial bodies of liquid. We also see evidence of dissolution features, places where, whether through rain or other erosion properties, things have been dissolved away. And we also see dunes. Now, we're not sure what these are made of either. We have some theories, we have some guesses, but it would be really nice to go back there and look at them, and I'll talk about that in a minute. Now, as a chemist in the lab, Titan is a really complex system, so is Earth. How do we deal with that? Well, we can break down some of the processes that are happening and just study them one at a time and really understand that really well and then try to see how the pieces map to the whole. So we were interested in looking at these lakes and evaporite playas, and we asked the question, what happens when things evaporate from a Titan lake? And so how do we do that in the lab? Well, let's take a look at Titan. So this is an image of the North Pole. It's just taken by Cassini using some near-infrared wavelengths that get through the methane window, so you can actually peer all the way to the surface. Here are a few of the lakes, which are a little bit hard to read. Ligeia Mare, Kraken Mare are two of the biggest ones. But if you zoom in on this region, you'll notice that these phase bright areas, these sort of orangey bits, we call them evaporite because that's what we think is how they're being made. They tend to form in and around lakes that seem to be receding or drying up. And so we were interested in studying that in the lab. Well, in the lab, it's actually not too hard to make a Titan lake. Titan's atmosphere is about 1.5 bars, so it's a little bit thicker than Earth's. and it's nitrogen rich, right? Well, okay, and the temperature is 90 Kelvin. Well, liquid nitrogen temperature is 77. So what we can do is make a liquid nitrogen bath, heat it up a little bit from 77 to 90. That boil off of the nitrogen is now generating your nitrogen atmosphere, and hey, you're halfway to Titan already. So that's a basic principle behind how we can simulate some of these environments. We can make these lakes. We can also look at smaller samples in what we call a cryo stage, which is just a fancy container where we can hook up liquid nitrogen, precisely control the temperature, and be purging with nitrogen gas on the inside to, again, replicate Titan's atmosphere and also prevent water condensation and other things that tend to happen when stuff gets cold. If you've ever pulled a frosty beer mug out of your freezer, you know, it's not frosty till you pull it outside, right? And then it gets all of that frost forming from condensation. So we want to avoid that in our experiments. And so we've done some experiments like this. This is one example. We took benzene, which is not good for us to breathe in. If you ever notice that sort of yucky chemical smell whenever you're filling your car with gas, that's usually benzene. That's part of that smell. It's a liquid here at room temperature, but at Titan it's a solid. And it's a nice white solid. What we did here is we took a droplet of benzene and we froze it. And so what you're seeing is sort of the edge of that crystalline droplet. It crystallized when we froze it down at Titan surface temperatures. And then we dumped liquid ethane on top. Now, typically, when you are working with cryogenic things, cold things, not a lot happens. At least not a lot happens fast. When you cool things down, reactions tend to slow down or stop completely. It tends to be pretty boring. But in 15 minutes, we saw this, right? We saw these beautiful crystals over here broke up into little bits. And I didn't do anything. I didn't just like take it and shake it over my head and like, no, I didn't do anything. And this happened spontaneously, which is really fascinating to us. And so we decided to study this with spectroscopy. And what we found, now this is a type of spectroscopy called Raman spectroscopy. Basically, any peak that you see is representative of two of the atoms in the molecule vibrating or twisting or doing some sort of torsion or something like that. But usually you'll see some characteristic peaks for a few different things, like right here in the middle, these are for ethane. But you see that dashed dotted green line? There's a new peak that grew on that blue spectrum, right, after we let these guys sit together for a while. That tells me that there's some subset of the ethane population that's in a different chemical environment than the rest of the ethane around. Now, why would that be? What could it be doing? Well, whatever it's doing it with benzene, because some of these benzene peaks are shifting too. That's weird. Okay, well, let's see if we can study this some more. We looked at what happened when we heated this up. And what we noticed was that all of the regular ethane goes away. All these peaks right here, they go away. But this little guy, he hangs out up to, gosh, almost 165 K, which is still frigid here, but that's a big deal for us. That means whatever that separate population of ethane is, it's in some way that it's protected, that it can hang around longer even when you heat things up. Well, these are our two building blocks, right? You've got benzene, your nice 6-carbon ring, and you've got ethane. Well, what can you make out of those two things? Well, we went back to the literature and we looked, and it turns out there's something called a co-crystal that happens between benzene and another molecule called acetylene, which is pretty much the same as ethane. It's just given up a couple of hydrogens and it's got a triple bond instead of a single bond. But we were like, okay, well, maybe it looks something like this. 2 dinner plates, you know, with an ethane sandwich in between. Well, luckily, we have a friend down in Australia who has access to a synchrotron, and so we were able to do cryogenic X-ray diffraction and neutron diffraction of this sample, and our best guess was completely wrong. So picture benzene, which is like a dinner plate, right? Instead of the sandwich, no, take 6 of them and like put them on their sides, kind of in like a circle, and then put the ethane molecules down the middle in like a tube. That was what happened. So this is essentially our first discovery, what now we're calling a Titan mineral, because that's basically what it's doing on Titan's surface. This is like a hydrated mineral, right? Because ethane's liquid there, which is kind of cool. Here's another view of it. If you sort of like drape over the ethane molecules, or the benzene molecules, you can see the tube structures better. Now, this is sort of in the same class as a clathrate, except a clathrate is a closed cage, right? This is open on both ends. Still really weird, but this explains why the ethane was hanging around longer. It was like happy in these little tubes, just chilling, and you know, you could heat it up a little bit more and nothing would happen. So is this unique? or can other molecules do the same thing? Is this the only example of a Titan mineral? Well, if we're starting to call them minerals, probably not, right? So we went back to Cassini's data set, and we were talking with a colleague, Dan Cordier, who he'd been doing some modeling of looking at like, okay, well, what else could be dissolved in a Titan lake? Like what is really abundant? What would be the most soluble in a Titan lake? And if you look at it, I know this is kind of complicated looking, but you see the blue lines that say C4H10, that's butane. You know, butane lighters, butane. And then the green line that says C2H2, well, that's acetylene. If any of you have ever used acetylene torches, that's, you know, it's not that complicated, right? Just don't light it on fire and then you'll be fine. Turns out that those two molecules, chances are some of the most common ones on Titan's surface. And guess what? They form a co-crystal too. So this is relatively recent. We just submitted the paper on this. Acetylene and butane also interact together and hang on to each other and form a unique Titan mineral. Now this one's a little bit more interesting for us because this would probably be a lot more abundant. There's not a ton of benzene around on Titan, but there is a lot of acetylene and a lot of butane. And so this could be something that we could see all around in the Titan lakes. And it may affect things like dissolution properties, how things erode, stuff like that. In fact, it could even be a way to sort of keep hydrocarbons hidden away in some kind of reservoir. And that's something that, in terms of astrobiology, we need to think about. It's not just what kinds of materials may be available, but we may need to be thinking in an entirely different regime of chemistry, right? Here on Earth, the way that most of our cells work, the way we exchange energy with ATP, adenosine triphosphate, is we have to make and break a covalent bond to do that, right? You have ATP with 3 phosphates, and you cut that PO bond, and then you pop off one of the phosphates, and now you have adenosine diphosphate, right? And that's that energy. You get a lot of energy from making and breaking, or from breaking that bond. But on Titan, here, making and breaking a covalent bond at these temperatures is like really hard to do. So maybe instead of a covalent bond, things like hydrogen bonding or pi bonding, things that are much, to us, like weaker bonds and lower energy may end up being the currency that life could use. And so when we are looking at some of these environments, especially the really unusual ones like Titan, we need to think even more outside the box in terms of life and what might qualify as life and what life might use, which is kind of cool. Okay, and then the last thing I wanted to talk about is, because I did mention, boy, it would be nice to go back to Titan. Titan does have a tremendous amount of organic complexity. We've seen molecules in its atmosphere with Cassini all the way up to like 10,000 Daltons and above. That's big. That's like protein quality, large molecules. So it's got this inventory, and we don't yet have a really good handle on what it is. Oh, come on, play. Please play. This is my favorite video. Come on. There it goes. Wait, no. Ah, okay. All right. It's going. It's going. All right. So you know how on Mars we had the 7 minutes of terror? Well, for Dragonfly, we're going to have about 100 minutes of mild angst because the atmosphere is a lot thicker, and it takes about 100 minutes for us to get all the way through it. We're going to leverage a lot of what Mars has done in terms of the sky crane landing architecture. Because the gravity is 1/7 and the atmosphere is 4 times denser, it's actually more efficient to move around the surface in a series of sort of flying hops with something like Dragonfly than it would be to drive around traditionally like you would with a Mars rover. So Dragonfly will be landing in or near Selk crater, which is close to the same latitude as the Huygens lander. So we will be able to collect some data that we might be able to compare in terms of atmosphere and initial surface readings back to Huygens. And will be very exciting. No, I don't want to play it again. No, can we keep going? Let's keep going. Come on, don't do this. All right. So I'm really lucky to be a part of this mission. I don't have to call it a concept anymore. Yay, because it was picked. And thanks to a lot of the automation technology around drones and being able to fly these unmanned aerial vehicles, there's a lot we can leverage in terms of being able to navigate and have this type of autonomy on Titan's surface. Remember, given the one-way light time from Earth to Titan is going to be anywhere from 64 to 86 minutes, depending on where exactly we are. It's not like we can control this thing from Earth. So a lot of autonomy is going to be required. But we think we have a really robust concept, and apparently NASA does too. Again, space is big, so planned launch is in 2026, and right now we're baselining an 8-year arrival until we get to Titan, 8-year transit. So in 2034, don't do the math and see how old you'll be, because you'll probably be depressed. But I will be very excited when I am 51 years old and we are landing on the surface of Titan. The strategy in terms of selecting a landing site was really challenging, because Titan's surface is so variable. There's so many different features, and we wanted to be able to explore all of them over the nominal 2.5-year mission that Dragonfly will be there. We selected Silk Crater because it has a lot of different components relatively close to each other. There are very few craters on Titan's surface. The atmosphere is so dense that it would have to be a really big comet or meteor in order to make a dent. Luckily, there were a few, and Silk Crater is one of them, so there may be some exposed water ice bedrock that we'll have access to. There are some dunes nearby, which will be really fascinating to finally find out what those are made of. There's also potentially some interdune material and some ejecta blanket from that impact that we would be able to look at as well. So the current baseline plan for how Dragonfly will operate, it'll have sort of a base station that it takes off from. It'll go and cruise at about 400 meters and go and scope out its next landing site that the science team and, of course, the engineers have all assessed for safety. But before landing there, it's going to go and scope out its next site and then come back and land at its new site. So that way, every time that we take off, we're already thinking sort of what the next step ahead is, and getting some data in terms of topography, high-resolution images, and things like that to make sure that our science team and our engineers have plenty of time for future mission planning of where we might go next. There are a lot of science objectives that Dragonfly will address, including prebiotic chemistry. We'll have a payload that will be able to look for various organic molecules through both hard and soft ionization, so we can even look for the big things. Our mass range is going to be much bigger than anything that Cassini had brought, or Huygens for that matter as well. We'll also be assessing the habitability of Titan and its many environments. We'll be including a meteorologic package as well as seismometers to try and understand, are there Titan quakes? How is the interior connected to the surface? What kind of exchange processes might we expect? And then we will be searching for biosignatures, whether they are there or not. And I wanted to leave plenty of time for questions. So if you have any other questions about Dragonfly or any of the other things I've talked about, please don't hesitate to reach out. And with that, I will thank you very much for your attention.